Hello, my name is Chieh from Northeastern University. Today we're going to talk about solving semi-definite programming via low-rank factorization based on the paper called A Nonlinear Programming for Solving Semi-Definite Program via Low-Rank Factorization by Monteiro and Burer. Now, semi-definite programming are problems that I think the standard form basically looks like this, where we know A, I, C, and X. These are all matrices. B is a scalar, and these are all known. So like any other optimization problem, we are finding the X that essentially minimizes this expression. Of course, we have other constraints, such as this right here. This is set of constraints. And there's a bunch of them, like essentially M of them. Is that X must be positive semi-definite. That's what that means. Positive semi-definite. So we have learned, well, actually we have not learned, but the general idea is that there are many different kind of convex relaxations, such as rank could be relaxed into a nuclear norm. Cardinality could be relaxed into L1. These are very difficult to solve, and these are much easier. So we can actually just convert rank optimization criteria into nuclear or L1 norm. Now, SDP problem is another kind of relaxation that's often used for NP-hard problems. So I'll give you a very quick example of one of these problems. And the famous one is called max cut problem. Let's say you have 4 nodes, 1, 2, 3, 4, and they all have distance to each other. Written here, the distance is 1, distance is 6, from here to here, distance is 5. So the idea is you want to separate them into 2 groups, such that 2 groups of nodes, such that the distance between the 2 groups are maximized. So you want to separate into 2 groups and want to maximize the distance between them. Now, let's look at some cuts. Well, we can cut it this way. And if we cut it this way, let's look at the distance. The distance is 5, 5, 6, and 1. So this distance is 12. Now let's cut it this way. If we add up all the points, 1, 6, 6, 1, 1, 6, 6, 1, 14. So this is a better cut because we've increased the distance. Of course, ideally we want to cut something like this. And we'll get 5, 6, 6, 5, which is 22. Notice that this is the max cut. Now you can imagine as we get more and more nodes, more and more, instead of just 4, we can have a lot of them. And there are a lot of combinations which you can do to cut. So this is also very useful for if you want to do clustering. Obviously, you want to separate things into 2 groups such that their distance is maximized. That's basically like clustering. So this is normally an NP-hard problem. Relax it into some kind of SDP problem. So the ability to solve SDP is useful when you run into some of these NP-hard problems. If I have time, maybe later on I can do more detail of how this can be turned into a SDP, like how a max cut problem and SDP is the same thing. But today we're just going to look at how to solve this problem efficiently. So traditionally there are many ways to solve this, but based on this paper, there's a more efficient way of solving it. So given a standard SDP problem, here's the standard one, right? The one that we just saw. How do we solve this? Well, maybe we can try writing out the Lagrangian. So when in doubt, write out the Lagrangian. So the Lagrangian is pretty easy to write. Here is the function. Over here is essentially the conditions. The hard one here is how do we deal with positive semi-definite constraint? How do we deal with that and turn it into some kind of Lagrangian? Well, we know that if it's a number, for example, x, this is not a matrix. Like here is a matrix, But let's say x is just a value. It's greater than 0. What we would normally do is turn it into x less than 0 and set that condition with some kind of lambda x. We would normally do it with just a scalar. And with a matrix, actually, it's very similar. You end up getting a negative trace x, where S is a matrix as well. And for this, to make this more clear, I think why don't we go over how that came about. So how do we represent the positive semi-definite constraint in the Lagrangian? Well, let's go with the definition. What does positive semi-definite mean? Well, it means that for any vector v, v transpose xv must be greater than 0. So if we pick vector vi, v1 for example, this must be greater than 0. Let's pick another one, v2, then v2 transpose xv2 must also be greater than 0. Obviously, if we add them together, if individually they were greater than 0, adding them together, they should definitely be 0. This expression can be written this way. Now, when we do the trace, notice we only sum the diagonal, right? So if we sum these two, it's the same as that expression over there. And then we can actually factor them out. Once we factor them out, notice that when you xv1, xv1 is right here, and each one of them, if you multiply them out, we have this expression. And lastly, we can just call this v transpose and call this v. So this is equal to this expression. Now we can do a rotation. Like when you have a trace of v transpose xv is actually equal to trace of v transpose v transpose x. So I move this over here. They're actually equal to each other. Now that is something you have to look it up or prove yourself, but it's good enough if you just look it up on the table. That's what it will say. Well, once you rotate that, we're going to call this matrix S. Right? That's S here. And notice over here is greater than. We can convert to less than by putting a negative here. Right here. And this S, notice that it has to be positive semi-definite and symmetric because of where it came from. It came from a multiplication of two matrices multiplying with its own transpose. Okay, so now you kind of see how positive semi-definite constraint is basically equivalent to minus trace of Sx, where S is some matrix. Well, let's try writing the Lagrangian again, now that we know this. So again, this goes here, this right here goes here, each with its own Lagrangian multiplier. Notice this is actually a scalar value. And this one goes to here, where S is actually matrix. So we can now write out the Lagrangian, right? The next, we want to define the KKT conditions. With the KKT conditions, the first is the primal feasibility, dual feasibility, because that's the dual, and then complementary slackness, and as well as we want the gradient to equal 0. So these are the conditions. If these four conditions are met, it means that we have found an optimal condition. Obviously, we want this to be met. That's one of the constraints. And this are also very important. So let's solve for the gradient, where the gradient of the Lagrangian with respect to x is equal to 0. Because it will reveal some interesting insights later. Okay, so here is the Lagrangian. If we take the derivative, well, if we ever take the derivative, trace, this right here is going to be equal to basically this. Like, this is something that you will have to look it up on the table again, or memorize it, or basically mathematically prove it, which I've done. But in any case, notice how this became C. This is a constant. That just comes here. And this becomes S. And that's the gradient. That's it. And once you have that, essentially once you have that, oh yes, this is the Lagrange multiplier. So we want to move this over here. And now we have an equation that essentially tells us what S is. Okay? And at this point, like the traditional way is we can use this thing called interior point method. But the point of this paper is to say that there is a better way to solve it. Okay? Problems with solving a traditional semi-definite programming problem, if you try to solve X, well, X is n by n, so it's pretty big. It could get really big, actually, so it's time-consuming to solve, and it takes up a lot of memory because X is a big matrix. Also, positive semi-definite is an annoying constraint. Maybe we can get rid of it. Lastly, very often X is a low-rank matrix. So maybe it's a better idea to take advantage of this fact. So the paper proposed yet another approach. Instead of solving X, right, the paper proposed that we solve R, where X is equal to R transpose. So notice R is a low rank. It's much, much smaller than X. But X is a big matrix. So since X is positive semi-definite, it implies that this is always possible. As a matter of fact, this implies that X is positive semi-definite. Also, notice that R is a significantly smaller matrix. So it's easier to solve because it's smaller, it's faster to solve, and use up less memory. Also, since we got rid of R instead of to R transpose, we don't need the positive semi-definite constraint anymore. It just implies this automatically. So the new problem becomes that this is the old problem. There you go. The new problem, notice that all the X turns into R transpose. And that's it. And the theme of this paper is that by solving this problem here, by finding the optimum location of this problem, it is the same as satisfying the optimal condition. So over here, remember we had used the KKT condition, whereas over here, we're going to end up using a second order sufficiency condition, which essentially just says that we want the gradient to be equal to 0 with respect to x and lambda, and we want essentially the Hessian. That's really simplifying it, but essentially the Hessian to equal to a positive definite matrix. And we want to show that by satisfying these conditions, we simultaneously satisfy the KKT condition of the original problem. So we're going to satisfy these. When we satisfy these, the KKT conditions we were looking at before, here, well, I can't find it anymore, will also be satisfied. So that's basically the point of the paper. Let's look at the first condition. So here's the problem. And like always, when in doubt, you just write out the Lagrangian. So the Lagrangian, this goes here, and this goes here. Now, I equals 1, 2, m. So there are m conditions here. So the first thing I do is I multiply here and multiply here. So you see, they're separated. And then I combine the trace. Now, like always, you know, trace of A plus trace of B is equal to trace of A plus B. So you can see I combine two traces into one. Now, notice over here is RR transpose. So I pull it out. And now remember, the original condition, what S was. Remember, this was S, and S was symmetric. So this is the same as S. Okay? So if we just call this thing S, right? We call this S, the fourth KKT condition. Gradient of the Lagrangian. So if that's S, then we're all good. So notice I have set this thing into S. Once I do that, I can rotate this R to this side, so it's easier to find the gradient. And if we find the gradient of this, of course, there's no R here, so this cancels out. When you find the gradient of this, it turns out to be this. Because, well, S is S transpose. So that, yeah, keep that in mind. And this is something that, again, if you don't know this, this is something you have to look it up on a table. And the table will tell you, or you have to memorize it. So since S is some, Lagrange multiplier, bake the 2 in there. And it doesn't really matter because this whole thing equals to 0. So I could get rid of that. So there is the other condition. Well, interesting. If we remember the 4 KKT conditions, right? We satisfied this one because S is equal to that whatever that thing was, and we just said it that's S. And then after that, we realized that, this is the complementary slackness is also satisfied because, well, if X is R times R and SR is equal to 0, then 0 times R is equal to 0. So the complementary slackness is also satisfied. Of course, the primal feasibility it's obviously satisfied because you see, because X equals to this. If this is satisfied, this must also be satisfied. So we now have 3 conditions satisfied, right? This one satisfied. This one satisfied. This one satisfied. So all we have left is the dual feasibility. Now all these we met with the first order condition, right? We did this and we satisfy a whole bunch of them. Now the second condition, essentially you want the Hessian to be positive definite or positive semi-definite. Now if we take the derivative again of the gradient of the Lagrangian, we get the Hessian. And we get the condition that the Hessian must also be positive semi-definite. So notice that by satisfying, if we satisfy the second order condition, we also satisfy the dual feasibility, right? When we satisfy this, we satisfy the dual feasibility. And in this chart, it basically shows that different things that we write out satisfies different conditions. So we have basically shown that this problem could be converted into this problem and that they have the same optimality condition. Now that we have shown that they are the same problem, how do we actually solve it? Well, the paper proposed to use this thing called augmented Lagrangian, which I am going to assume here that you do understand augmented Lagrangian, which takes this term here, this term here, but twice, adding a square. If you haven't gone over augmented Lagrangian, it might be a bad idea to try to understand this paper. But you do whatever. And then we use dual ascent to solve it. Lastly, we know that, well, X equals to this, and R is some smaller matrix. But we actually don't know what Q is. Well, so what is Q? Well, we don't really know. And it could be anything between 1 to n. So if X is this big, n by n, it could be as small as this or as big as the same size. So the paper suggests to just start with a low number and test it as you go up, 1, 2, 3, 4, and keep increasing Q until all the conditions are met. Of course, this kind of sucks, but I guess that still gives you a good result. And they did give us a theoretical limit that Q times Q plus 1 divided by 2 is bounded. It's actually bounded by the n value. So if they're not a lot of condition m, right? They're m of these, then we basically have the situation under control. So here's the general idea. I hope this helps when you are actually trying to read the paper later, because there's a lot of derivation that may not be obvious. So all right, thanks for watching.